Okay, this is a nice report that's been put out independently by a few scientists. So it's called State of the Carbon Dioxide. This is the first edition, and it's Global Independent Scientific Assessment of Carbon Dioxide Removal. It's a collaboration between University of Oxford, German Institute for International and Security Affairs, and Mercator Research Institute on Global Commitment and Climate Change, and University of Wisconsin Madison. Obviously, the topic is hot and worth looking at. It's quite long with 9 chapters. I'm going to take some points from the executive summary and few additional points from each chapter, which is on introduction, the research landscape, the innovation, public perceptions of CDR, carbon dioxide removal, policy making to make the transitions and deployment, scenarios for the future to meet the various scenarios, global warming targets like 1.5, 2 degrees C by 2100 with 67% probability, and the gap where we are headed right now and where we need to be to meet those scenarios and the future assessments. There are lots of references, very nice long list that you can look up. So I'll read a few points from the executive summary just to start off, and then we'll start looking at some of the figures, which are always, a picture is worth 1,000 words. So, scaling up carbon dioxide removal is an urgent priority as our efforts to rapidly reduce emissions if we are to meet the temperature goal of the Paris Agreement. Drawing together analysis across several key areas, this report is the first comprehensive global assessment of the current state of CDR. Secondly, we find a gap between how much CDR countries are planning and what is needed in scenarios to meet the Paris temperature goal. This is like the emissions gaps reports we have been looking at. However, there are currently few plans by countries to scale CDR above the current levels, exposing a substantial shortfall in terms of where we need to be and where we will be if we don't change our ways. For the first time, this report compiles an estimate of the total amount of CDR currently being deployed around the world. Actually, we have seen this in other podcasts as well, in terms of what are already implemented and what are planned out to, let's say, 2030, and how much CO2 is being drawn down by these current implementations. In the near term, several countries plan to maintain or slightly increase conventional CDR on land by 2030, which is on its own a huge challenge requiring dedicated policies and management. So the conventional CDR typically depends on land use types like afforestation and prevention of deforestation, restoration, and so on. Before we move to some more points, let's look at one figure just to avoid the monotony of reading stuff. Only a tiny fraction of all current carbon dioxide removals result from novel methods. What are the novel methods? So here they are: BECCS, bioenergy and carbon capture and sequestration, biochar, and other novel CDR methods. And one has to be careful because in another podcast I've talked about relying on these technological promises for the future goals of decarbonization, net zero, global warming targets, without having a full guarantee that these will be attainable in terms of scalability. So almost all current carbon dioxide removal, which is just 2 gigatons CO2 per year, comes from conventional management of land, and a tiny fraction, 0.002 gigatons CO2 per year, results from novel methods. So here you are, almost all of it is from conventional land methods, and here is a tiny fraction, 0.002 gigatons CO2 per year, coming from what are termed here as novel methods. Carbon dioxide removal is a feature of all scenarios that meet the Paris temperature goals. We are relying on those technological promises to get to our warming targets, in addition to, of course, reducing emissions, which is not so great, because if you look at CO2 emissions from the Keeling curve or other sources, you see that despite the 25 years of negotiations, There was a temporary dip in COVID lockdown period, and of course there are financial crises which have driven dips, but you bounce right back, so that's not going so well. Carbon dioxide removal in 2020 and in the 3 Paris consistent scenarios. So here you are in 2020 at 2 gigatons CO2 per year. Virtually all current carbon dioxide removal, we said, is coming from conventional management of land. And if you want to see where we are headed in 2030, 2040 or 2050, focus on demand reduction, 48% of the gas reduction by 2030 here. Focus on renewables will give us 31% of greenhouse gas reductions by 2030, with large uncertainties on maximum and minimum potential along those pathways. And focus on carbon removals, 33% greenhouse gas reductions by 2030, which will get us here by 2050 to around, let's say, 10 gigatons CO2 per year with these contributions, and huge uncertainty here in terms of where we may end up, similar to current numbers or much larger than the current numbers. So there is a gap between proposed levels of carbon dioxide removal and what is needed to meet the Paris temperature goal. We already know that. So level in 2020, again 2 gigatons CO2 carbon dioxide removal. Proposed levels compared to the 3 Paris relevant scenarios in 2030 and 2050. So here is 2030, here is 2050. Look here again on the country's pledges in the gray shaded regions, which go up a little bit, but if you look at where we need to be, with focus on renewables accounting for 5.4, focus on carbon removal giving us 3.9, focus on demand reduction giving us 3.5. So closing the gap requires scaling up carbon dioxide removal, particularly in the next decade. Is this already at a high technology readiness level? We'll see a table that these are mostly technological promises as such in terms of scalability to reach those numbers. By 2050, focus on renewables compared to what the long-term strategies of the countries are, which would give us 2.9 by 2050, still a tiny number compared to where we want to be, where we have to be. Focus on renewables up to 7.6 gigatons CO2 per year. Focus on carbon removals would be 9.8 gigatons CO2 per year, and demand reduction has to meet 4.7 gigatons CO2 per year. Obviously, there are technologies that have to be available. BECS has to work. Policies have to be in place, implementation mandates have to be met, and so on. Coming back to the points from the executive summary, the figures are also from the executive summary. Closing the CDR gap requires a rapid growth of novel CDR. So this is where the technological promises come in, and the uncertainty and the lack of guarantee that we will have scalable novel CDRs available. CDR is not a silver bullet even if we meet these goals, as scenarios that limit warming to 2 degrees C or lower require deep cuts in emissions in addition to and not in place of CDR. So CDR may give people a sense of security that we can keep emitting and somehow we'll keep removing the CO2 and hide it somewhere else, a geological storage, etc., which we will look at in a minute. But that's not the case, that we must come out of this carbon trap, as we have talked about elsewhere, and build a system that is essentially only down to irreducible carbon emissions and net negative to remove those irreducible CO2 emissions. Of course, there is also the other greenhouse gases like methane and 2O, etc., which have to be included as well, because the global warming targets always have to consider CO2 equivalent. You remember how we did that, you can look up in the other podcasts. So keep that in mind as well. The next decade is crucial for novel CDR in particular, since the amount of CDR deployment required in the second half of the century will only be feasible if we see substantial new development in the next 10 years, novel CDR's formative phase. Okay, there are lots of other words that I'm not reading, but the report is available online that you should definitely go and read up. Now, there is a gap between proposed levels of carbon dioxide removal and what is needed to meet the Paris temperature goal. So we are again looking at 2030 and 2050. So here the numbers are slightly different because we are now looking at so here we looked at what is needed to meet the Paris temperature goal. So you can see here it's 9.8, for example. Here it's at 6.3. So just be mindful of the differences. Conventional carbon dioxide removal proposed levels compared to 3 Paris relevant scenarios in 2030 and 2050. So again, the country's pledges are here at 2.6, and we long-term strategies are only at 2.3. So we have to increase the drawdown from renewables, CDRs, and demand reduction with a much larger increase out to 2050 on all these three. So the numbers are there. There are uncertainties associated with them, but basically the point is we are not on track to meet the Paris Agreement goals right now. Okay, novel carbon dioxide removal proposed levels compared to 3 Paris Agreement scenarios. So let's read the text later on. This is coming from new technologies. This is from conventional technologies that we talked about. So new technologies, new novel CDR methods have to add to renewables, CDR, and demand reduction. So few scenarios involve no novel CDR but require even more aggressive emissions reductions, which we are not on track to achieve. Okay, basically the current pledges and long-term strategies are ridiculously small in terms of the focus on novel CDRs compared to what is needed. So those are the different numbers, conventional versus CDR. So those numbers add up. 6.3 and 3.4 will give us basically 9.8. Okay, that's how it is done. Reading more points, the peer-reviewed scientific literature on CDR is growing faster than for climate change as a whole, now consisting of over 28,000 English language studies. We'll look at some numbers, including how public perception is shaping up. Innovation in CDR has expanded substantially in recent years. I have podcasts on the ignition for nuclear fusion, for example, and if nuclear fusion becomes technology ready to be implemented as small reactors and utility scale reactors, then that could be a massive game changer in terms of removing coal and other fossil fuels from electricity generation, for example. CDR is becoming more of a public talking point too, although awareness remains low relative to other aspects of climate change. So it's too much for people to deal with, that there are extremes happening, health issues, food security, water security, energy security issues everybody is facing, and then there is on top of this CDR being talked about. So people have to constantly be on their toes for awareness, with lots of information being put out, like this podcast, for example. The primary policy implications of this first assessment of the state of CDR are that meeting the Paris temperature goal requires us to accelerate emissions reductions. This is obvious for anyways. Increase conventional CDR and rapidly scale up novel CDR. Easier said than done, but we have to put these down. The principles of used in this report. Principle 1, the CO2 captured must come from the atmosphere and not from fossil fuel sources. The removal activity may capture atmospheric CO2 directly or indirectly, for instance, via biomass or seawater. So you can do ocean alkalinity experiment, iron fertilization, etc. to put it into the ocean, or you can use BECCS bioenergy and carbon capture and sequestration, where atmospheric CO2 is being captured by photosynthesis, and that biomass is used to do carbon capture after it's used for energy. Principle 2, the subsequent storage must be durable such that CO2 is not soon reintroduced into the atmosphere. So this is very critical, and there is time scale for which it has to stay out of the system. The removal must be a result of human intervention additional to Earth's natural processes. So this additionality is very important. If you put down a forest, you have to show that the forest is actually additional to what already exists, and it is actually sequestering additional carbon compared to what nature would have done anyways. So additionality is very critical. This could include other techniques like natural climate solutions or nature-based climate solutions like agroforestry, grazing land management, and so on and so forth. Okay. To be defined as a CDR, a method must capture CO2 from the atmosphere by principle 1 and durably store it according to principle 2. Here are some examples. An example of a method which satisfies both principles and hence qualifies as CDR is afforestation and reforestation, which is here. There are several approaches that satisfy only one of these principles and hence are not CDRs according to the definition used here, but which count as carbon capture and utilization, for example direct air capture to fuels, or as fuel carbon capture and storage. So that's what we are looking at here. So in the afforestation, atmospheric CO2 is captured if you increase coverage and reforest or afforest. You have additional carbon going in, meeting principle 1, and then biological storage can then count as complete CDR. In the example of direct air capture, you may end up converting into synfuels and synflue and so on, where you are using it in producing polymers, various industrial applications, fuel use, where you release that CO2 back. So this doesn't satisfy principle 2. And in the use and storage, you have where you are extracting fossil fuel. So stored carbon is extracted, and sometimes captured CO2 is used to increase pumping out fossil fuels in what is called enhanced oil recovery, and then the utilization of that for whatever activity is associated with carbon capture and is stored here. So this fails in principle 1 because you are removing stored carbon and not taking CO2 out of the atmosphere. So all these are important. Generally, the global carbon cycle consists of 5 main carbon reservoirs: the atmosphere, land, products, the things we produce which have embedded carbon, and ocean and lithosphere. So those are geological formations. Within each reservoir there are various carbon pools indicated here in each reservoir, whose characteristics vary in terms of storage capacity and durability, or the time scale. For example, if you put it into the bottom of the ocean, it can get metamorphized into rocks, limestones, etc., and stay for geologic time scales, whereas land soil carbon has much shorter durability. Carbon dioxide removal methods transfer CO2 from the atmosphere into other durable pools within the global carbon cycle. So there is a natural global carbon cycle. So land has, of course, crops, agri-forest residues, trees, wetlands, and soils. Atmosphere has a pool that we measure very easily and precisely because it's well mixed, long-lasting greenhouse gas. Products include concentrated CO2, fuels, chemicals, biochar, aggregates, and woods in wood and construction. Ocean, of course, has dissolved CO2, aquatic biomass, standing stock, marine sediments, which are a huge sink, and bicarbonate, which, depending on how the process works, can be re-releasing CO2. So there is a uptake and release in each of these. And lithosphere, of course, has depleted fossil fuel reservoirs, saline aquifers, and minerals like calcium carbonate, which have a carbon pool, right? Timescales, the durability of different carbon storage pools ranges from decades to tens of millennia. Note that these timescales are indicative, assuming no premature disturbance. For example, trees and soils are subject to huge perturbations, and tropical forests are often sources of CO2 rather than sinks because of perturbations, including wildfires, which are often you know, made worse by climate change, which is related to human activity as well. Wooden construction, again, not permanent, but you can see the scales here. Can be 10 to 1,000 years. 10 to 1,000 years. Biochar can be much longer, 10 to 10,000 years. Marine sediments can be also 100 to 1,000 years. Geologic formations can be 10,000 to 100,000 years, and minerals also 10,000 to 100,000 years. Okay, so these are again assuming humans are not digging up everything and releasing those carbon dioxide. So I will stop this podcast here and spend the next podcast reading the table here in detail, which is a summary of CDR methods, and it's worth reading. If I start here, it'll take too long, so I'll make it as a separate podcast. Okay, so let me stop this here and we'll come back and continue.